Professor Zhang, please. Thank you.
Good morning, everyone. I'm Professor Hua Zhang from City University of Hong Kong. Welcome to a series of virtual academic seminars to celebrate the launch of SmartMat. SmartMat is an open access journal co-launched by Wiley and Tianjin University. I'm one of the co-editors-in-chief. The other one is Professor Wenping Hu from Tianjin University. Today, Professor Ning Wang is an invited speaker. Before his talk, let me briefly introduce him. Professor Ning Wang is a chair professor of physics and a director of Center for Quantum Materials at the Hong Kong University of Science and Technology, HKUST. He obtained his PhD degree in materials physics from the University of Science and Technology, Beijing, in 1990. In 1989, he received an Alexander Humboldt Research Fellowship and worked in the Institute for Metal Physics, Göttingen University, and the Fritz Haber Institute of the Max Planck Society, Berlin, Germany. In 1993, he joined the physics department of the HKUST. Professor Wang's research interests focus on the fundamental issues of materials physics, particularly 1D and 2D quantum material device fabrication and property studies. He has authored and co-authored over 280 research papers and received Qingsheng Wu Jianxiong Physics Award, State National Science Award, and Achievement in Asia Award. Today, he is going to talk about probing quantum transport in atomically thin transition metal dicotyl semiconductors. Let's welcome Professor Wang to give a talk. Professor Wang, please.
Okay, thank you, Professor Hua Zhang, for the introduction. I would like to thank the invitation from the editors of SmartMat, a new open access journal focusing on materials, and congratulations on the launch of SmartMatter. I wish this new journal very success. Okay, my talk today is about 2D materials, atomically thin transition metal dicotyl semiconductors. It's also called TMDC semiconductor. And they're interesting quantum transport properties. So we have been working in this area for many years, and those students, PhD students listed here in my group, have made a great contribution to this research. And I would also like to thank my collaborators working on theoretical and experimental parts of this project. So my presentation will focus on three parts. So after a short introduction, I will first explain how to make a high-quality, high-mobility TMDC field effect transistor devices. That's very important for measuring the quantum phenomena in this material. Then I will give two examples on the unconventional quantum Hall states and the magnetic field. So in the last part, I will show you some pretty interesting structures and the transport properties in Moiré superlattice from twisted TMDC. So in 1950s, Professor Feynman has pointed out that layered materials is an interesting system that could offer an enormously great range of possible properties for material. If we could really control the arrangement of atoms on a small scale. So following on the great success of graphene research, two-dimensional atomically thin layered materials, such as the MDCs, semiconductors, have attracted great interest. So when we're talking about the property of 2D materials, we need to know the structures and the chemical elements. So traditionally, we use growth techniques to form the structure we need, but that is limited by the principles or the mechanisms of crystallography and thermodynamics. And in recent years, people use a so-called exfoliation technique, artificially stacking of new structures, provide more opportunity to control the material structures, in particular for 2D, and have a new degrees of freedom for great potential applications. So my talk is focused on, let's say, the TMDC. So let me introduce very roughly about the structure-wise of this kind of layered materials. The stable structure or phases are so-called semiconductor phase. It's hexagonal. Yeah, it's hexagonal. It's stable. So we call the 2H phase. It's because of the stacking. And you can use Scotch tape method to exfoliate this material to get a monolayer, bilayer, trilayer, and so on. And another phase is metastable. I mean, but you can obtain it from physicists, from other techniques. For example, there's a metallic 1T or the 1T prime, the topological phases, and so on. Yeah. So this kind of phase is formed based on 2H through we call it distortion of lattice position. Exfoliation method for this TMDC actually have been developed, already well known. People use Scotch tape and exfoliate pretty thin materials, this kind of materials. That means the interlayer coupling is weak. And I mentioned about this 1T or 1T prime, there's a distortion phase. So if we look through the cross-section views, you see the typical features as I marked here. Yeah. The so-called 1D phase is simply the shift to the right side from top layer, and you form this regular distorted structures. Or you make further distortion like this, partially distort structures, or further distortion, and you get a 1T prime or 1TD. And those materials show superconductivity, so metallic properties, show the topological phases because of a band structure, very recent. So go a little bit details about the band structure. This is the fundamentals for measuring those unconventional quantum phenomena. So this is 2H stacking, okay, and you see clearly inversion symmetry here. Okay, so once you exfoliate this material into a monolayer, so it's mathematically break the so-called inversion symmetry. Okay. So in the momentum space, I list here the so-called valley, the energy maximum or minimum positions, or the band A's at different vectors. Let's say K prime, show 6-fold symmetry, 3-fold symmetry, and gamma points, the gamma valley, the center, and there's also a Q valley there. So for bulk materials, the band structure is characterized as so-called indirect band gap, because if you look at the Q values, it's lower than the K value. But for monolayer, the situation is different. So I listed here K value, gamma value, Q value, and that is the topic of today. And I gave you detailed explanations about the transport, about the spin states, Okay. The very important things in this kind of material is so-called spin-orbital coupling effect. Okay, for monolayer plus the inverse symmetry breaking, and that cause the band splitting. Let's say for conduction band, for example, the K, the spin up, spin down stays split, and at the valence band you have a similar situation. Okay, you may also call left and right hand spin. So this strong spin-orbital coupling effects cause the spin valley entangled states. So what do you mean? That means because of the time reversal symmetry, this K and K prime values are not degenerated. And at the lower energy states, the spin up and spin down occupy K and K prime. Right? So you have a spin generated states, the KH, but they have offside spin polarizations. Now that gives rise to interesting properties that people use to study this kind of materials, such as controllable valley polarization or valley selective circular dichrosing. It is a polarizer and detect the light emitting from different bands. On transport study, this is a topic, the details I'm going to introduce, is that when you measure, for example, the quantum oscillations, and those electron behaviors is correlated. It's correlated to the band structure. For example, this Q valley. Yeah, Q valley, people studied for not that long time. There are 6 Q values, okay, and plus spin down, spin up, spin down. So the total degeneracy is 12. It's 12. That means there are 12 states. All right, and those spin states, I say this is a valley entangled. That means, for example, you have a even layer of materials, and then the spin up, spin down degenerate occupy at K at Q, and the total degeneracy is 12. So once you apply magnetic field, spin up, spin down shifted, and then the lower energy states Q and Q prime, totally the degeneracy is 6. But if you make a O layer, monolayer, tri-layer, this spin up, spin down stays already lifted. So the degeneracy is already 6. And once you apply magnetic field, the spin down, spin up shifted, and basically you only detect one of the values spin states, and that degeneracy is just 3. It's just 3. So that is the interesting states. All right. And if I show you the calculation about band structure, you should be familiar with this, and then understand what I'm talking about in transport. For monolayer, you have 1 band, monolayer, 2 band, 3 layers, 2 layers, 3 band, 3 layers, and 3 bands. But once you consider spin-orbital coupling, this 1 band split slightly up and down, and the valence band up and down. All right, and a similar situations happened for different layers. And if you look at the Q valley, once the layer number increase and the Q valley decrease, shift down. All right, so the challenges to measure the states through transport is that to make a high quality device. And in the past 5 years or so, different groups have made a great contribution to probe the small quantum studies in these materials. And next, I'll show you the very fundamental things, how to make a high quality device. Okay. So I'm going to introduce about this encapsulated structures by boron nitride, because boron nitride is ideal electrical materials using so-called dry transfer techniques. And then I'm going to demonstrate our unique technique we call the selective aging or phase translation to make a ohmic contact. So field effect transistor structure is pretty simple. Basically, you need a source and drain electrode connection here, and then you apply a gate voltage through a dielectric material, for example, boron nitride. And then you will see this on-off characteristic. And there's cross point, so-called metal insulator translator. On this kind of, in this kind of regions, I mean, when you increase the carrier concentration to the right side of this point, the material's behavior is metallic. Okay, metallic. On left side, it's insulating behavior. Right. And so far, people, for example, study the mobility, the FET qualities. That mobility compared to the graphenes is it's too low. The mobility for graphene normally can reach millions, 1 million, in that range. But TMDC is too low. So what causes the poor quality of this device? There are a number of reasons, like the impurity at the interface, whether your sample is clean or not clean. Can you make a real ohmic contact to the conduction channels? Is this due to materials problems or due to the vibration problem? So different groups work on this for many years, using different ways, like work function matchings, there's different annealings, there's phase engineering, phase change, and so on. Right? So the problems actually is happen at interface between the semiconductor and your metallic leads. Nowadays it's metals. So once the metal attached on a semiconductor surface, because of the dangling bonds, we call the chargeable studies, happen at the interface, and that causes the effect so-called Fermi level pinning. Fermi level pinning effect. So first proposed by Martin many years ago. And this tripping of the charge caused the high barriers, so electron injections get a high resistance. Basically, it's not possible to overcome this barrier. So it's difficult to inject current into the materials. So the way that you make ohmic contact is that to make a depinning, to make a clean surface, to passivate this dangling bonds or chargeable studies, so that the work functions can match between the semiconductor and the actual metals can match each other, right? Match each other. So people think about this for a long time and tried using graphene, for example, or heavily doped the traditional method, or phase engineering, and so on. But the results, the outcome is not that ideally. Still, the mobility is not high enough. People also think about that way to use an insulator between the semiconductor and metal leads, and so that these two materials cannot see each other, and there's no pinning, Fermi level pinning effect. And that's true. This can effectively reduce this pinning effect. But the problem, the drawback is that electron injections through channels have to through the tunneling effect. Tunneling. Yeah. And that limits the injection, carrier injection efficiency. So it's still a not good problem and not good solution. So if you look at the mechanisms, I show you a cartoon to show interface structures. So on the right side, the dangling bond, there's a high Jockey barrier. If I simply deposit materials, metal on top surface, because there's no bonding, there's no charge effect, yes, but there's a van der Waals gap. You have to inject current through the tunneling effect to the materials, and the efficiency is not high. Right? So the ideal solution is that if you can convert part of the 2H semiconductor phases into a 1T or 1T prime, anyway, it's named here distortion phase transitions, and that phase is metallic, and then use metals to make contact on this metallic phases and make ideal junctions. So if look at the details of the bands, the minimum bands and the conduction band here, for example, that's if it's a 2H phase, the lowest state is the D is a 2. I mean, there are the two states, spin up, spin down, occupied by electrons, and then there's no extra electrons, and that's the reason that they have semiconducting two phase. But if you make a distortion, the minimum states actually is partially occupied, and that's the reason you see a metallic phase. All right, and if you make such junctions, from lattice structure or bonding point of view, it's a similar. It's the idea. Now, in it, we make such a connection and achieve very low contact resistance, for example, for 3-layer molybdenum disulfide the channels. So our approach based on this. Now, first we use encapsulation structure because boron nitride is clean. If you make a sample directly on silicon dioxide, that's called the charge impurity scattering. The probabilities cannot be high. So the boron nitride is ideal. And then we use a selective agent to make lattice distortion and make deposit the metallic state electrons. So let's show you the principle. We can use the MMA to pick up a boron nitride and then pick up TMDCs and make sandwich structures and then make a pattern, okay, make windows, and so that oxygen can directly interact with the material and cause the phase transitions. So this is the principle. Molybdenum disulfide is pretty stable in air. So we use oxygen plasma can quickly make the window through a boron nitride and then cause the phase transition. I'll show you the details. Then the next step is that you choose a perfect metal with the matched work function to the conduction band or valence band. Then you can make ohmic contact. All right. So this is the device, and this is the principle. So once again, I saw the image, this simulation image of a so-called 2H 1T phase. Right. So the principle is that we make sandwich structures, and then at each area we make window and make a phase change to metallize the channel materials. So I show you one of the high resolution, atomic resolution of this device and the interface between the 2H and the so-called 1T phase. And then this is a titanium we deposited. You can see titanium electrode directly connect with this area, the edge area. But you see something happen at the edge area. So this is the enlarged picture of atomic resolution. So we point out the atomic positions, and you see the atomic distance changed, shorter, longer, shorter. That's the typical feature of 1T or 1T prime. So is it 1T or 1T prime? It's hard to say, but distorted there. And on left side is 2H. is 2H. So this is the model that actually we make a 1T bridge between the semiconductor and the electrode. Okay, and next I show you the transport property. Is this a good ohmic contact? Yes, we measure for different materials for N-type and P-type. So you see a pretty nice curves on the off. And importantly, if you look at the mobility that we can achieve in the WIC2 structures, it's about 300,000. That mobility is already comparable to those of a high quality graphene, right? And you see nice quantum oscillation. This quantum mobility is also very high. Yeah. So based on this kind of structures, this kind of devices, we probe very nice quantum phenomena in these materials. So I use this chart to show the progress on making on improving the mobility of this TMDCs. So in 2016, the highest mobility we make is comparable to those of TMDC device based on graphene contact. Right. So in last year, we further improve the mobility to get one order of magnitude higher. So the next, I show you these two examples. Yeah, two examples. The first one is pretty easy. So if we make a nice device and we turn the Fermi level, and then we can change the Fermi level to the conduction band. So we measure the electron behaviors, or we turn this to valence band. Here we can say gamma or K, and then we see nice oscillations. Right, and this is the feeding factor, and from this you can see the degeneracy and so on. So before I go further, I provide you quickly go through about fundamentals of the so-called quantum Hall effect. So the so-called quantum Hall effect happened in traditionally in 2D materials, 2 dimensions. And in high temperature, you have a diffusion transport. This is you can use that standardization to describe this phenomena, diffusivity. But at low temperature, electron behaves like wave, and then you see this the so-called quantum phenomena. This quantum is so-called phenomena is so-called the quantum phenomena is the wave behavior. Yeah, and in traditional classical Hall effect, you increase magnetic field and the Hall voltage that you measure across sample increase linearly. So quantum phenomena is the plateaus. You see plateaus. Those plateaus represent the so-called Landau level. Those high-speed electrons inside the your 2D, and you apply magnetic field for cyclone motion. We use a harmonic oscillator to describe this phenomenon. So electrons occupy at different energy states, and it's called Landau level. And we need to measure this Landau level through 8 states, because bulk inside 2D materials is just insulated, probed by transport. So at H, you have a band H crossing Landau level, and that region you detect this Landau level transport. So Landau level, this is a Fermi energy surface, and this occupies states. Once you apply magnetic field, so yeah, Landau level forms, and in each Landau level, there are 2 states: spin up, spin down, spin up, spin down, and so on. Yeah, and in the following data, I show you one thing about the G factor. So what is the G factor? G factor represents the separation between spin up, spin down state in each Landau level. Right? So it's called lambda G factor. that represent the electron interactions in states. So if there's no interactions, it's just a simple particle pictures of the particles, okay, then the G factor is 2. That means the separation between the up and down state is just mu b. Yeah, mu is the boron magneton. It's a constant. But if something happens unusual in the states, the G, it should be very large, or should be very small, but normally it's very large. Yeah, then I show you this. So give it 1 turns filling factor. Filling factor is the states degeneracy. So the 0 lambda level, there are 2 states, and the next 2. So 2, 4, 6, 8, and so on. This is a filling factor. All right. So experimentally, we can measure this lambda level energy gap and the so-called Zemath gap is related to the G factor. So basically, we determine G factor, then we know the interaction effect in the materials. All right. So the quantum states that you measure is basically you set the energy Fermi levels in the gap, that is plateaus, but in the lambda levels, you see a peak and so on. Yeah. So if the quality of the material is not good enough, you see first the Cherenkov oscillation that represent the same things. So I'm going to introduce one thing. It's about the spin susceptibility, basically the G factor. Yeah. How to measure this? This G factor is represented by the ratio of Zemath energy and the spectral energy at the level. Okay. That represents it's actually the response of the degenerate interacting electron once you apply the magnetic field. All right, so this is the principle. This is the principle. And I show the first example is this. All right, so you measure the oscillations. Basically, each peak represents each lambda level. You can identify the filling factors. And once the magnetic field large enough, you see spin up, spin down, spin up, spin down. And that is represent the Zemath energy. Zemath energy, right? And we can determine other parameters like effective mass, degeneracy, and so on. So they have to do the analysis. If you look at the filling factor, it's a little bit strange. You have all filling factor. So in last slides, I say normally have a paired, and this should be even filling factor. Why does it have a odd filling factor? That already indicates the unusual states in this state, in this materials. So I give you this figure to show the principle how to measure the ratio of Zemath energy and sectional energy. So if the Zemath energy is not large, I mean the G factor is not large, and then you can actually use this figure to show that the filling factor is even. All right. But if I tilt the magnetic field or tilt samples, this ratio is changed. Now first, Zemath energy is assumed is unchanged and independent of B field tilting. It's determined by the total magnetic field. But the synchronous energy at the lambda level formed in the planes, it depends on the B component, magnetic field component perpendicular to this. So once I tilt, this two energy gaps will cross, and eventually I can determine the angle and determine the ratio, and then I can determine the G factor. All right, G factor. So this G factor also shows this. This is spin up, spin down. You have lambda levels. So if the Zemath energy is so huge that you see this situation, this is the Zemath energy. That's 3 times larger than the cyclotron energy. Then you have a chance to see such kind of old filling factors. So this is the principle. And what caused this? There's many reasons. We need to further study that, like strong electron-electron interaction, or the values, things, and so on. So it's the beginning. So then here is the data that we perform this sample. Now, the aim is that to identify the ratio, or I list here the first crossing point, second crossing point, and third crossing point. Right? And in principle, we should see the lambda level patterns, shift, split, and inverse intensity, and so on. All right? Yeah. And that's the experiment data. So we measured it. And we do identify this crossing point, the crossing point at 23, 45, 55, 54, and so on. Yeah. So we identify 3. But the problem is, how do you know this I is 3, 4, 5? It's not 1, 2, 3. The principle is this. If I assume the first crossing angle is I equals 1 and 2, 3, and then plot it in this simple relations, there's not in a linear line and across 0 point. Now, unless you put this, the first crossing point is 3, and 4 and 5, they perfectly align to each other. So by this way, you determine the G factor. It's about 6. It's about 6. So single particle pictures is 2. So that indicates strong interactions from behavior in this kind of materials. The next one I'm going to show you is about the K situation. We studied the K value, Q value, gamma value, all things. Yeah. So in K value, the interaction is even stronger. The G factor is over 20. It's a carrier concentration dependent. So for K values, it's a little bit complicated compared with previous one, gamma value. Gamma value is simple. It's just 1 gamma in 1 Boolean zone. But for K, you have K prime. So basically, there's 2 electrons occupied at 2 values, but they degenerate. They occupy at the same lambda level, and you detect both. Yeah. But the principle is quite similar. It's quite similar that this time it's not tilting, but the ratio of this, ratio of Zema energy and cyclone energy, they are carrier concentration dependent. Yeah. So once we change this ratio, change N, and then we can measure the crossing point, the 4, 5, 6, and so on. And you will see blue and red is spin up, spin down, but from different values. And the low filling factor, for example, 1, 2, 3, is just isospin, like magnetic, ferromagnetic. Okay, and then in others, in higher states, is mixed spin up, spin down. All right, so I'll show you this map to give you the experimental results, and so that you understand the principle that if, for example, for high filling factors, you have spin up, spin down, spin up, spin down, then until 6, 4, 5, 2, 3, 2, and 1 is isospin. This is isospin. It's like this polarized region. That's called the ferromagnetic translations at high magnetic field. And then we further determined splitting of this energy gap and determine the G factor is really high. So in the future, if you want to study the materials and you want to explore the electron interactions, behaviors, this is a good candidate material. All right. So in last part, I show you one more thing, and pretty interesting, the hot topic of Moraes politicus in twisted materials. I demonstrate two things. So one is superconductivity signature. And the second is giant non-linear Hall effect center. All right. So a simple introduction about twist materials is basically 2 years ago, published by the MIT people group, Moiré pattern and graphene. So once you twist 2D, two-dimensional materials, two layers together, you form at small angles, the Moiré superlattice unicells. So in the momentum space, you will see the small brilliant zones. Okay? So theoretically, people calculate the band structures. In addition to the values that I demonstrated, there are more so-called the flat bands, the mini bands. It's not flat, but it's called flat bands with a narrow gap. Right? So people make a device for the twist structure and then calculate the band structure change, the density states, distributions around Fermi level. And once you change gating states at a certain feeling. So what do you mean feeling? You count, you feel electrons, how many electrons per unit cell. That's mean feeling. For graphenes, there are 4. You need 4 atoms to feel per unit cell, and you get 4 feeling. So at certain feelings, you see very nice curves of superconductivity. That means you measure resistance is 0. At certain, the so-called magic angle. Magic angle means when you calculate the band structures at a magic angle, it's a pretty flat, ideally flat bands. And this is also the evidence that you have energy gaps, superconductivity. That means the superconductivity persists still there until a certain high field. This is all the superconductivity signature. If you look at the conductance, this is the direct points. So normally you have a V-shaped of this valley's conductance. But once you twist at a certain feeling, this is a full feeling. Full feeling. I see conductance is almost 0. It's a very insulating. But at hard feeling, for example, here, hard feeling, you see a very high conductivity. Right? It basically is it's a superconductivity states. Once you apply magnetic field, then suddenly it's changed. It's break superconductivity states. So this is the material is interesting. It's the superconductivity is gate tunable. So before there's no report about such materials that you can use a gate electric method to turn the superconductivity and the insulating state. People call this a mode state, but actually this is still debates whether this is insulator or outer phases, right? The superconductive phase. And for TMDC, theoretically, there are similar things. You have Moiré pattern, and you can feel electrons. For example, the states. You may have still have a insulating states, and you may have a mini bands here. Yeah, once you place the Fermi level at this stage, it could be topological insulators and so on. Yeah, so they're pretty rich physics that you can explore using this kind of materials. And one thing is also important that TMDC has very strong electron-electron interaction. In fact, that graphene normally does not have such effect. I show you some data. For monolayer by monolayer, it's all the unpublished work. And you see nice phase transitions once you change the gate. Gate means the character concentration. You see superconductor transitions to 0. No major angle. Any angle is okay. Will do. So this is the another example at 1 degree. Then you see some superconductivity studies right there. But the curves, it looks really complicated. It's really complicated. What caused this? Yeah. And we also detect the values. We have, this is the 2 plus 2, double by layers, already 4 layers. So in principle, we should detect the gamma value behavior. So we study this double bilayer twisted samples using the different approaches, APAS, for example, and then plot the pattern. And based on this mechanism, we discovered a giant nonlinear Hall effect. All right. So this is the twist WIC2 samples. So here are superconductor states. So once we have a half filling here, all right, this is some insulating behavior. So we study the materials at this region. So what is the barrier curvature related property? So barrier curvature is already well known. You can read some very fundamental textbooks. It's a so-called geometrical properties of anything. You make integrations and see whether it's 0 or non-zero. Normally it's 0. Normally it's 0. Okay, and for some materials with without inversion symmetries or strain induced in materials, now you can see these terms. The barrier curvature. Barrier curvature acts as a magnetic field in momentum space only. Yeah. So you can imagine that if there's magnetic fields, we call this pseudo magnetic field, then the electron behaviors will be changed, like Hall effect. And indeed, previously we have studied the so-called valley Hall effect. So what does it mean? That means in this inversion symmetry breaking system, there's a strong barrier curvatures, okay, and the electron behaviors at different values feel different forces in momentum space. So that's effective mass field, effective magnetic field. And this spin up, spin down is from different value, as I introduced. All right. So those two kinds of electrons will go in opposite way and accumulate voltage. And once you detect the measured voltage, that's the Hall voltage, and divided by the current you injected, that is called resistivity or conductivity. All right, so this is the principle. And previously we calculate the let's say monolayer. You see a pretty strong barrier curvature because there's no inversion symmetry, and bilayer inversion symmetry restored, and you see a nice there's no barrier curvature. Trilayer, see again, you detect the intrinsic properties of Hall effect. Twist material. So this is the equation written by Professor Yao Wang from Hong Kong University. They explain it that way. In momentum space, you see this kind of terms. Okay? In real space, for discrete materials, you see a similar terms. Okay, you see similar terms. I say for homogeneous materials, you have immersion signature breaking. You see this barrier curvature terms, and that causes the let's say valley Hall effect and so on. And in the spatial inhomogeneity, in this kind of Moreau patterns, that causes additional terms. Now, this term is similar to the barrier curvature, okay, and that behaves like a magnetic field. So this is the plot of the pseudo-magnetic field in this kind of materials. So some years ago, people already published if you highly bend the materials using a particle and have a monolayer, a graphene, and others, that causes a very strong magnetic field related to the string gradient. It could be very high, 100 Tesla and so on. Okay, so the principle is this: we can make a nice device and then try to measure the Hall effect. I mean, we inject current here, but then measure the voltage across here, but using different frequency. Theoretically, this is a barrier curvature curves. If you introduce extra strings, as I demonstrate there, the sample is always inhomogeneous, but then that causes the barrier curvature dipoles. Okay, it's not uniform. The barrier curvature dipole. Barrier curvature dipole can be interpreted based on the first order momentum of barrier curvature. The zero order is so-called Hall. The previous one I show you the valley Hall effect and so on. The first order barrier curvature is called barrier curvature dipole. The short figure is something like this, right? This is a direct vector, and this result in a second harmonic Hall response. I mean, once I use a frequency omega and I measure at perpendicular directions using 2 omega, you detect a very strong signal. That's exciting. And theoretically, people can use this formula to this term. This is the electric field and the barrier curvature dipole terms, and will generate the second harmonic signal. Okay. The nonlinear Hall effect is normally weak. Previously, people discovered that in WT2 and string OS2 and so on. Right? And the non-linear Hall effect voltage, what we detected, is much higher than those discovered in these materials. 6 order of magnitude higher than those materials. Very exciting. So I show you the experiment data quickly. You see, this is a current I inject through, for example, this sample 2, 1 to 2. And I measure voltage through probe 3 and 4. And you see the nonlinear relation. This is the voltage at 2 omega. This is 1 omega. Right? We have different sample. We have a 1 to 1, 1, 2 to 2 to 2, 3 plus 3 at the same angle. For example, the 2 degree and 2 degree. All right. So this is the band structure. The barrier curvature dipole happened at here. Conductivity and the band. Monolayer, tri-layer. All right. So we can make a device, circular, to detect all directions of the Hall voltage. And surprisingly, we detect all signals in all directions. And that is different from previous one. Previous one, they have a mirror symmetries, and then perpendicular to the mirror directions, it will see 0. But this is not. This is not. Yeah. And there's a term called response barrier curvature dipole can be experimentally measured if you know some parameters. The voltage that we measured, and the sample width we know, the conductivity or resistivity, and the current, and tau is a reaction factor. That can only be estimated. And then we measure the dipole, the barrier curvature dipole. So at certain feeling, you get a very maximum. At certain feeling, you get a minimum. So This axis is the feeling, and the color means the intensity. Intensity. All right. So what do we learn from this experiment? The broken rotational symmetry and mirror symmetry will separate the barrier curvature with different signs, and resulting this so-called barrier curvature dipole near the Fermi level. That is different from uniform materials, right? Uniform material. And you have this extra string called the barrier curvature dipoles. That's the region that you detect the 2 omega, the second harmonic oscillation frequencies voltage across sample, perpendicular to the electric field. Perpendicular to the field. So the device is nice, okay, and you simply inject one frequency, you detect double frequency. Okay. So the nonlinear Hall sigma is normal to the source, but it's parallel to D, parallel to the dipole positions. All right, so you can estimate the dipole values. The experiment data is roughly around 2 to 3 or to 4 nanometers, roughly in that region. There's experimental errors. And then we calculate one important parameter. It's called responsivity. That is the ratio between the nonlinear Hall voltage and the applied source power. That means I apply a very small power. How large is the voltage that I can detect across the sample? Look at here. That number is huge. So we use the terms giant nonlinear Hall effect. Paper is not published. But we put this on the archive in this part. So if you want to learn more details, you can take a look at this sample of this paper online. And this number is 6 order of magnitude higher than the so far reported nonlinear Hall effect. The problem is that how to explain this? We need a theoretical groups to work together on this. So far, we do not have conclusion, but we know something related to this very interesting Moreau pattern formed by twisted TMDCs. Yeah, you may ask, any people observed such a nonlinear Hall effect in graphene? So not yet. If you have interest, do it. You should see it once you can reduce the strain. But the key point is that if you want to introduce maximum strains, you need a small angle. You need a small twist angle. All right. So come to this summary. So today I tell several stories. Now, one thing is about the interfacing, electrically interfacing the ohmic contact for this semiconducting TMDC. That's the key for your further studies. So you need to achieve ohmic contacts and then achieve as high as possible mobilities. And then I demonstrate 3 things. Those are the G-factor issues. Just want to show you that its materials have strong electron-electron interactions in Q valley, in K gamma valleys, in K valley, in Q valley. That's really good. Yeah. And then in twisted structures, you see pretty rich properties, superconductivity, insulating transitions, jet, nonlinear Hall effect, and so on. All right. So time is up. I would like to stop here, and thank you very much for all online audience. Thank you very much. And any questions?
Oh, Prof. Rao, thank you so much for the wonderful talk. Before we start the Q&A section, I just briefly introduce our journal. SmartMat is Professor Wenping Hu and Professor Hua Zhang. The scope is quite broad. Topics include but not limited to organic and polymeric functional materials, shape memory alloys and polymers, 2D materials, interactive polymers, biomimetic robotics, smart textiles, electro-rheological and magneto-rheological fluids, AI and neurophobic devices and systems, metamorphic biomaterials, self-healing materials, piezoelectric materials, and artificial muscles. Now we're open for submission. Welcome to publish your excellent work in SmartMat. So now we are going to start the Q&A section. The first question is, in the device, is it possible to use materials other than the boron nitride?
Yeah, this is a pretty good question. We have a
Well, we cannot hear.
Maybe there's a problem for internet.
Yeah.
Let's wait for a while.
Okay. Oh, wow. Hello.
sorry.
Yeah. Sorry. We didn't hear the answer for the first question. So maybe you can.
Now I'm back again. There's some trouble. Can you hear me?
Yeah. Now it's okay.
Yes.
Yeah. It's automatically switch off, but I don't know what's the reason. Did everybody hear my answer to the question?
Sorry, Prof. No. So could you please?
No. Okay. Then I need to repeat it.
Sorry.
The question is about the boron nitride that we dielectric materials we use for the device, right?
Yeah.
Yeah. So according to our experience in past of so many years, boron nitride so far is the best dielectric materials for all this kind of 2D materials, exfoliation prepared by exfoliation method. If you prepare the device using other dielectric materials, it's called trouble, mainly from charge scattering. So do not use silicon dioxide as the dielectric materials. Now, the charge impurity is too strong, and that cause the influence your transport measurement. All right. So if you want to achieve high mobility devices, do use boron nitride. That is the ideal materials. Yeah.
Okay. Thank you, Prof. The second question is how to control the formation of distortion in the structure.
All right, this is also a good question. People use a mechanical method to introduce distortion. All right, that is the simplest way. So for twisted materials, no matter graphene or TNDCs, if the angle is below 2 degrees, roughly around 1 degree, this distortion automatically introduced. Yeah, automatically introduced. Yeah, please.
So the sub-question, what will be the future development and the challenges for TMDC?
What's the future
development?
Future
development and the challenge.
Okay. Yeah. The future development is that we still want to improve the quality of the TMDC channels by improving the mobilities. Okay, and there's still room that I believe the mobility of TMDC can be comparable, definitely, with those of high quality graphene and so on. Okay, and the main challenging issue is that TMDC is not that more robust compared to graphene. Okay, the graphene is indeed really strong, really robust. You can use different approach to clean surface and without introducing defects and so on. But the TMDC, be careful. You can easily introduce, let's say, vacancies or add atoms to TMDC. But the good thing is that TMDC is semiconductor with gaps. Yeah, graphene has no gap. You need to extra electric field to introduce the small gaps. But TMDC has pretty large gaps, and some properties like variable effect can survive basically roughly in room temperature also. But for graphene, no way. The gap is too small. So there's some advantages and also challenges. Okay.
Okay, thank you, Prof. Wang. Due to the time limitation, the Q&A section will be stopped here. If you have further questions, please email us. We can forward to the speaker. Okay, so please let's thank Prof. Wang for the wonderful talk again. And welcome to submit your excellent work to SmartMat. It will be our pleasure to publish your work in the journal. Thank you so much, and see you next time.
Okay, thank you. Thank you very much. Thank you, Professor Zhang. And
谢谢啊。
general invitation.